Welcome back to STEM Online Academy. This is Jason Masterakos. For those of you who don't know, STEM Online Academy is a YouTube channel in which we help undergraduate students taking advanced mathematics, physics, or engineering with term help for the entire term, midterm, studying hard questions for midterm and exam test. Okay. So today we're going to be looking at the electric field of a finitely charged rod, and particularly the symmetry that a lot of students miss. Okay. Now, most students don't lose marks on this problem because the integration is too advanced or the mathematics is too advanced. They lose the marks because they start in the wrong place. Okay. So if you try to solve the electric field of a finitely charged rod by starting with the integral first, as I have here, this is the particular integral that we're going to be looking at, okay? It's going to feel downright, um, well, if you start with the integration without knowing where it comes from, it's going to feel downright ugly. And the problem is, it's not really about the integral, right? It's about the geometry, okay? Right? Because in physics, once you see that, the whole setup becomes much smoother and much cleaner. Okay. So in this video, I'm going to show you how to build, right? Build and solve the electric field of a uniformly charged finite rod at a point, right? At a point, a distance y above the midpoint without panic. Okay. Without wasted algebra, without missing any of the um, calculus, we're just going to get right to the physics first, okay? All right, so I think we should get right to it. The problem that we're looking at is this particular integral, okay? We're looking to solve that the electric field vector as a function of y is this integral from minus L over 2 to L over 2 of Coulomb's constant, k is Coulomb's constant, times the linear charge density lambda times y dx all over x squared plus y squared all to the 3 halves. Okay. Now I did something different here. Normally when we do finding the electric field of a finitely charged rod, it's usually written as a word problem. Here, I've already posed an integral. Okay. Sort of like thinking backwards here. That's what I'm trying to get you guys into the mode of doing, is thinking backwards. How we got that integral, so you can make sense of where the integral comes from, right? If you know where it comes from, you will understand the physical phenomenon of electricity and magnetism. Okay, so you have to know where the equation came from. Okay, and that's where the physics comes in, right? If you understand the properties of electricity and magnetism, you understand where this equation comes from. Okay, so let's get to it. I want to state this clearly. So in this integral, you'll probably notice that the limits of integration are from minus L over 2 to L over 2. Okay, that is because we have a rod. Remember, the question is we have a finitely charged rod with length L. Okay, and it's going to be centered at the origin. I've made a drawing here, a visual diagram, so you can see how I'm doing it. Okay, so we have a rod of length L, as I've pointed out. My rod is highlighted in yellow horizontally, okay, with length L, and it's centered at the origin along the x-axis, okay? And just to let you know, x is the horizontal axis. You should know that, right? Positive x, and positive y, the vertical axis, okay? All right, so we have those. Now the rod is going to run from minus L over 2 to L over 2, okay? So that means that x is bounded between minus L over 2 to L over 2, okay? Because if the entire rod is length L, then if we cut right in half of the rod, it's split up with L over 2 and L over 2, okay? Where one is negative on the left side of the horizontal axis, one is positive. Now, you'll notice that it has a uniform linear charge density, okay? So this integral here that we're dealing with has a uniform linear charge density called lambda, okay? Let me highlight here. So this is my lambda value. Okay, that's my lambda. Now in the drawing, I see why the visualization is very important. I can go back and forth from my equation to the visual diagram. Okay, it's really handy to make sense out of what's going on. So our linear charge density lambda, okay, if you want the electric field, right, at the point 0, comma y, okay, 0, comma y, right, lies directly above the midpoint, right, of the rod, right, the midpoint of this rod, okay, let me just highlight here, is here. Think of this as the center of mass of the rod, okay? So the center of mass of my rod is located at 0, comma y coordinates, okay? I highlighted it right down here, the dot. That's my center of mass, right at the midpoint of the rod. Now, this diagram is going to explain how we get the following, okay? Right, so after drawing the electric field vector, because electric fields are vectors, right? From our infinitesimal charge, Q. So let me just go back to the drawing. Okay. We have dq. Remember, my infinitesimal charge has to be located somewhere on my rod. So my charge, my infinitesimal electric charge has to be located anywhere on my rod, but it has to be on the rod. It can't be anywhere else, otherwise it's wrong. Okay, so it needs to be on the rod. Okay, so I made my dq over here on my rod. Okay, all right, so that's where my dq is located. And you will notice that the infinitesimal electric field, right, cancels, right? It cancels in the x direction. Now, why is this? Anytime I have my infinitesimal charge where I put on my rod, okay? So I have to choose where on my rod my infinitesimal charge dq goes, okay? Right from the charge, the infinitesimal charge, I have to draw from my charge to my electric field, okay? That's the case. You always have to do that, right? I've even written it down here, right? After drawing the electric field vector from the infinitesimal charge q, right? What ends up happening, so here's my dq, and I drew this blue line, that's my infinitesimal electric field vector, okay? That electric field vector, right, dE, okay, is made up of xy components. There's a y component going vertically upwards. You see that's my dEy, right? This is dEy, okay? Pay attention, this is dEy. Now, dEx is horizontal, right? One's going this way in the x direction. The other component of dEx in the infinitesimal electric field in the x direction, in the opposite direction. But you'll notice one is minus dEx and one's positive dEx. So the infinitesimal electric fields will cancel in the x direction because one's positive, one's negative. So it's only the infinitesimal electric field in the y direction we want. Okay? Let me say that again. The electric field cancels out in the x direction, right? Because you can see, based on the location of our infinitesimal charge, we have to draw a line to our infinitesimal electric field vector, okay? That vector is made up of x and y components. Based on the geometry, the y component is preserved. The x components are canceling because one's positive, one's negative. That's why the field in the x direction is completely wiped out. I hope that makes sense. Okay. Now, what's important about this, right? We want the electric field at a point of just above the midpoint of 0, comma y. 0, comma y are coordinates, okay? All right, so 0, comma y are coordinates. Now, how do we get that electric field vector that they gave us in the opposed problem? How do we get this mess? It still doesn't explain how we're getting all of this. Well, there's a reason. The reason is we use Coulomb's equation for an electric field, right? That the electric field of a continuous charge, let me be precise, continuous charge distribution, right? This is not finite charge distribution. It's a continuous charge distribution. That's why we're integrating, okay? So integrate K. K is Coulomb's constant times the infinitesimal charge, dq, all over r squared times r hat, where r is the distance. Let me go back to my diagram here. R is the distance, right? From dq, right? All the way to that midline there at the point which created the infinitesimal electric field vector. Okay, that's this distance here. I'm highlighting in white here. That's this distance. Okay, hopefully you can see where I've made my drawing. Okay, now from there, the electric field, right, is equal to the integral from minus L over 2 to L over 2. That's obvious, right? Because we're actually finding the integral with respect to x, right? You can see that the way that based on the geometry of the problem, based on where the rod is flat in this case, it's horizontal to the x-axis, where dq, the infinitesimal charge element, is somewhere on the rod. And we're drawing a vector from dq to the electric field. And since dEy is the only preserved electric field component in the y direction, everything else is canceled. So that tells us that we need, right? We need to find, hint, hint, we need to find the infinitesimal electric field in the y direction. Okay? That will make sense in a moment. All right? So I have my electric field as a function of y. Okay? But if we're finding this in terms of y, it turns out our integral has to be with respect to x. Okay? Now, this infinitesimal charge element, you should know that this is equal to lambda dx. How do I know that? How do I know this is lambda dx? Well, because of obvious reasons. Okay, the linear charge density, right, is equivalent lambda. Linear charge density lambda is equivalent to dq, the infinitesimal charge element, divided by dx. dq dx is equal to lambda. It's a derivative. So if I solve for dq, I get lambda dx. Okay, that's where I got this part, and then divide by x squared plus y squared. That is just using math. Okay, this part is the mathematical part of the problem, is the fact that here is a right angle perpendicular bisector with the rod. Okay, so you can see y is the height, x is the distance. Right? Okay, so I hope that makes sense. So we have that now. Okay, so x equals y squared, Pythagorean theorem. Now our hat, what is our hat? Our hat is a vector, but it's the vector that is pointing in the appropriate direction of dEy, because remember, dEy is the electric field that is preserved. Only the y component is preserved. Otherwise, it wouldn't make any sense, right? The electric field in the x direction is canceled based on the properties of the fact that the charge was located on a horizontal rod. Okay, so I think it's pretty obvious. So the r hat is just the definition of sine theta. Sine theta is equal to y over r. Okay, over here. So sine theta is y over r. Opposite side over the hypotenuse. Hypotenuse is r, distance r here. R from d is the distance from infinitesimal charge dq to the point, just at the point, near the point of the top of the vector of dE. Okay. Now, as I said, charge is dq equals lambda dx. That is our differential. Okay. Now, the distance from the charge element dq to the point 0 comma y, right? As I mentioned, is r equals the square root of x squared plus y squared. This is where the math comes in. Okay. The reason why r is square root of x squared plus y squared, as I said, Pythagorean theorem, is because here is a perpendicular bisector. So I'm using Pythagoras. Okay. So Pythagorean theorem. Okay. Now, since we have that, by Coulomb's law, right, the magnitude of this field, right, will produce, right, it's going to produce something really interesting, this tiny piece, right? So we want to think of the magnitude of the electric field, okay? Now, the magnitude of the electric field is just going to be, right, without the integral, let's think backwards. That means it has to be the differential electric field element. Okay, and that's equal to Coulomb, right? Coulomb's constant times dq divided by r squared, and that is equal to k lambda dx all over x squared plus y squared. I think that's straightforward. Coulomb's constant times charge density times dx over x squared plus y squared. Okay, this shouldn't be nothing. I'm not doing anything super complicated, right? This should be rather straightforward. Okay, so as you can see there, I've already figured out that factor. Okay, that's my dE. But that tiny piece does not point straight upwards, right? It only, as I said, it points along the line, okay, joining the charge element, right? The charge element to the coordinates 0, y, right? Along the charge element. So if my line, my electric field vector, dE, is there, I will make a yellow line. No, I like a green line or something, green arrow, yellow arrow over here. The point that this is r hat, and r hat is pointing in the direction of the electric field. Okay. So we need to resolve that entire vector dE, right, into xy components. Right? This is where the diagram matters, right? So if you notice, right, we have the horizontal leg, the x, vertical leg, the y. Okay, for the hypotenuse is going to be r equals square root x plus y squared, as I said, due to obvious symmetry. Horizontal components and x and negative x cancel, so only the vertical component of the electric field is satisfied. I'm repeating myself multiple times to make sure that it is clear that dEy is the only thing that is preserved. Okay, so dEy is preserved, dEx is not. Right, so dEy. Okay, so we've got that fact out of the way, right? This is the first major relief point in the problem if you think about it. Why do I say that? Because we don't need the full vector component, the full vector field, my mistake, full vector field component by component on both of the axes. We only need the vertical component. So we don't need to do the extra math on the dEx, only the electric field on the y. Okay? So let's do that. Okay. Let's look into more detail. But before I do that, okay, let's get to it. Right? I want to explain why the horizontal components are canceling. And I need to emphasize this because quite often students rush. They take two equal charge elements, right? Take two equal charge elements, one at x and one at minus x, okay? Now, if you do that, they are the same distance from the point 0, y. So they produce electric fields of the same magnitude, right? Let me repeat. They produce electric fields of same magnitude, but the horizontal components of the electric field are in opposite directions. That's why they're canceled. Okay? Doesn't get any more clear definition, explanation than that, right? Equal opposite of components of the electric field, x components. So they cancel, and their vertical components are just pointing upwards. So that just adds up. Okay? And that is why the net electric field has no x component, right? The symmetry of the rod, okay, and the location of the observation point will eliminate the horizontal part completely. Okay, and this is the kind of physics idea that, you know, just starts turning into algebra. And this is why, right? This is why I always use this technique when it comes to solving physics problems. That, you know, it should be, when it comes to problems like this, the most important thing is to start off with visualizing the phenomenon, okay, and then integrating. In other words, geometry first, integration second. Okay, so geometry before the equations. Okay, okay. So let's now build the vertical component correctly. Okay, I want to build the vertical component. Okay, let's build the vertical component of the DE, right? Vertical component of the electric field. We know that DE is this. So the vertical component will just be multiplying by a factor of y, right? Y over r, okay? Because the y component, I think it's pretty obvious, the y component of the electric field to be y over r, right? Multiplying by y over r, not y over r, but multiplying by y over r, okay? Because that will give us a sine. Okay, so sine theta is equal to y over r, opposite, over hypotenuse, which is equal to y all over the square root of x squared plus y squared. Meaning that my dEy, right? Remember from the diagram, right? My dEy here, okay. By the way, notice I made a mistake with my, a little mistake, my diagram, my theta should be over here. Let me see, yeah, just 1 second. Yeah, my theta was drawn in the wrong place. Drawn over here to get y over r. Yeah, y over r. Theta is drawn from the electric. Yeah, the infinitesimal charge element. Yeah. Okay, so we've got that. All right, so that there's my theta. Therefore, sine theta is y over r. R, just using the Pythagorean theorem, is square root of r squared square root of x squared plus y squared. And then my dEy, right? The differential of the electric field in the y direction is going to be dE sine theta. Okay, obvious, right? Sine theta for the y component. We substitute this. We substitute what we know about dE. Remember, dE is this guy. I'm highlighting with white here, with an asterisk. This is my dE. So I substitute the expression for dE into dE sine theta, which was the equation for dy. So therefore, I get k lambda dx all over x squared plus y squared times y all over square root of x squared plus y squared. Cleaning this up, I don't need to go into the math in detail. You should mathematically be strong at this, at rearranging the algebra, right? I'm just here to bring home the concept, right? So this is dEy, right? Now, hopefully that's making sense. Now, the total field, right? You want to be able to get the total field here, okay? The total field is once we solve for E of y. So that means we have to get rid of the differential electric field. We do that by integrating both sides of the equation. So if I integrate from minus L over 2 to L over 2, I'm integrating along the charged rod from minus L over 2 to L over 2 along the x-axis. Okay. So that is what we had here. And substituting that dEy for this inside in our integrand is why we get k lambda y dx all over x squared plus y squared to the 3/2. Okay, this is the integral we were given, but now it actually means something. Okay, you know how to get it, you know how to derive it, right? Because you're following and you're understanding hopefully the fundamental laws of electricity and magnetism. Okay? And this is important, right? The students remember methods better when the integral feels physically motivated and not just drop out of the blue, right? If you remember it, just but for the sake of memory, you will forget it. But if you actually understand how to get that integral, it means something. Okay. Now we can take a sigh of relief here. Actually, at this point, the physics is done. Okay, I've taken care of all of that. All right, all the physics is done. Now we just need to do some calculus, okay? Which is very relieving. And the hardest conceptual part of the problem is not the integration. Let's sort of mention it. So it's recognizing that the geometry lets us actually throw away the horizontal components, okay? Before the integral even starts. That's where the fun part begins. Right? So if this problem looked overwhelming before, it should already feel much more manageable now, right? You're not looking at some sort of mysterious formula and you just don't know like how on earth you get it. You're looking at the exact vertical contribution, right, of a charge element over the rod, of a horizontal rod. Okay. Now let's actually compute this integral, right? You'll notice here, now we're just doing calculus, okay? So if we evaluate the electric field as a function of y, as I mentioned, no more physics, just calculus now. So we're just going to evaluate the electric field as a function of y. This is what we had starting step by step. Okay, so now we're in, remember my systems method, visualize, model. We're now executing, okay? So we're executing the integral. So in order to integrate this, it's an integral that requires a trigonometric substitution or integration by tables. If you've taken calculus 1 or 2, you should have, otherwise this course would be a problem. So to do that, if you look up in the tables at the back of your calculus book, there's one here that says integral dx all over x squared plus a squared to 3/2 is equal to this. Okay, I'm just going to fast track it. I'm not going to go into detail why that's the case. You can also verify that if you want by using trigonometric substitution. Okay, but that's what our integral gives us. Now, here, a is y, right? Because if we integrate with respect to x, y remains fixed. It remains constant. So all a's are y's in this case from the formula. So then I get x all over y squared times square root of x squared plus y squared. Okay. So that's what we've got right now. Right. So as you can see, we're left with this guy. All right. So let's actually continue on the next page. After doing the integral, right, I get the electric field as a function of I is the Coulomb's constant charge, linear charge density times y times all of this mess. Okay. And if you recall, my bounds for the limit of integration were from minus L over 2 to L over 2 on the rod. Okay. All right. So the next step we need to look at fundamental theorem of calculus part 2, because the upper and lower bounds. Okay. So take the upper part and plug it in to x, because we're evaluating at x equals L over 2 and minus L over 2. So f of b is the first part, f minus f of a is the second part. Simplifying, you'll notice that the electric field as a function of y is just Coulomb's constant times linear charge density times the length of the rod divided by y times the square root of L over 2 squared plus y squared. Right? Pythagoras at the bottom, where I'm substituting all x's with L over 2's, right? And I collected like terms here, right? I simplified it. That's how I got this algebraically. I don't need to go through that. Okay, so this is what we get for our electric field, okay, as a function of y. That should be our answer. Okay, now, okay, sure. However, though, for those of you who are taking electricity and magnetism, you know it's not good enough to come up with an equation. Is that you actually need to prove / verify if this makes physical sense. Okay. That's the thing in physics. It needs to make both physical sense and also has to make mathematical sense. Okay. So let's check to make sure our answer actually does make sense. Okay. Case 1. We're going to evaluate our y from when y is way, way, way bigger than the length of the rod. Again, for the first case you want to do when dealing with calculating the electric field of a continuous charge distribution is to make sure that y is much bigger than L. So y needs to be much bigger than the length of the rod. Okay. So the way to do that, right? Let's look at the denominator. Okay, the denominator has the square root of L over 2 squared plus y squared. If y is dominating L, so think of it, y is much bigger than L, right? So that means over here, I can in reality say that L is going to 0. Right? So think of L going to 0. If L goes to 0, I'm just left with y, right? 0 squared plus y squared square root is y. So this is approximately equal to y. Well, then over here, look at my electric field equation. This part can all be substituted with y. Okay, so here's y. Okay, y times y is y squared. So I get the electric field as a function of y is equal to Coulomb's constant times the linear charge density times the length of the finite rod divided by y squared. Okay, that's case 1. Okay. Now, another thing too I want to mention is remember, we have to remember what Q is. Where the total charge Q is just the linear charge density times the length of the rod. Okay. Since Q is lambda L, I can replace this lambda L with Q, capital Q, the total charge. Right, I'm just zooming in here. Thus, my equation now becomes the electric field as a function of y is Coulomb's constant times the total charge divided by y squared. Okay, and so far that is correct. It is, because if you look at the definition of the electric field vector, it's Coulomb's constant times the product of the charges, or the total charge, divided by a distance squared. It's analogous to Newton's law. That's what Coulomb's law is for electric fields. Okay. Now there's case 2. This is when we're very close to the rod. So let's go back to the rod. Okay, let me go back to my rod here. I'm losing track of where my rod is. Okay, so as I said, right? As I said here, we want to get very close. So if y becomes very small, the denominator becomes small. Make y become very small. So that vertical distance y is collapsing. Think of the entire vertical distance starting to get smaller, 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 infinitesimally. So if y is getting incredibly small, the denominator becomes small, right? And if y is becoming small, then the electric field starts to get very big. Now, why does that make sense though? If y gets incredibly small, how come the electric field is getting big? Why is the electric field getting big? Why? Why is the electric field getting big? Well, think of it. If this y gets very small, right? Then this electric field vector, its magnitude will like spring out, right? Will really start getting ginormous. Okay, so this is making physical sense. Okay, right? And since case 1 and case 2 are making physical sense, and in case 1 we showed mathematically that the electric field is equal to Coulomb's law, then we've pretty much verified what our electric field integral is, our continuous charge distribution. Okay, so we have our continuous charge distribution. Okay? So this was pretty much what I like to call a sanity check. You know what I mean, right? Right, because if y becomes very small, denominator gets small, and the field is going to get very big, right? The closer you get to a charged object, the stronger the field, right? That's the reason, right? The closer you get to a charged object, the field just gets very big. It just gets stronger. It gets more condensed. The strength is more condensed the closer you are to the field. Okay, so our formula passes both intuition checks. So if there's anything I want you to take away from today's lecture, okay, about this, right, about electric fields of finite rods, okay, is one very important thing, okay, in terms of what students should remember for exams. Okay, there's certain things you need to remember for an exam. Okay, so I'm going to write this down. What you should remember. What to remember for exams. Exams. And I need to put an exclamation point to really bring it home. Okay. First, right? Do not start with the integral. Okay, so first, please do not, right? First thing, so you know what, I'm gonna use a difference. First, right? So first, do not start with an integral. Do not, I'm capitalizing this. Do not start with an integral. Start with integrals. Start with the integral. So don't start with the integral. You want to start geometrically, okay? Start with geometry. Okay, start with geometry. Because you need to visualize the phenomenon, okay? You have to first see it. If you don't see the phenomenon, you can't visualize it, the math becomes nonsense out of it, okay? So first, you need to start geometrically, okay? That's the first thing. Second, okay? So that's the first thing, okay? Second. The second thing I want you to do is ask yourself immediately which components are canceling. Ask, right? Which components are canceling. Okay. Ask which components are canceling, right? In terms of the symmetry, that's what I mean, right? There should be components that are canceling. If it's not the x, it's the y or x, okay? That alone, that question is going to save a ton of time and a ton of marks, okay? These two things are fundamental for understanding the electric field of a continuous charge distribution, okay? And number three, actually, yeah, there's a third point I should mention. Number three. So here's number three. Okay, so here's the third thing. Third, build the distance correctly, right? So build, right? Build your distance correctly. Please do this. This is so important. I know I'm sort of going over remedial steps, but these are the pain points and the most important points when it comes to these problems, okay? Number four, okay, so number four, the fourth thing, the fourth thing is project onto the surviving direction only, right? So project onto the surviving direction. Surviving direction. Okay. And that's the full strategy. And this is going to be reusable, right? All the time, right? The same type of logic will appear, for instance, right? If you deal with electric fields from rods, if you deal with electric potentials from rings, if you deal with center of mass problems, if you deal with moment of inertia problems, if you deal with magnetic field setup problems, all sorts of things, okay? This approach will apply for all these types of situations, okay? So if you struggled with problems like this before, the problem was probably not that you weren't good at uh, physics per se, I guess. Like sometimes it is, but I don't think that was the exact reason. You were trying to calculate before you actually built up the geometry, built up the visualization, built up the modeling. Okay, that is what makes these problems feel impossible, right? And it's a common problem, right? Everyone tries to calculate before they've actually seen the physical phenomenon. Okay, you want to see the phenomenon first, right? So draw your model correctly, right? And then calculate. But you need the model, right? So once the structure is visible, the calculus becomes much more reasonable. Right? That's why I focus so much on diagrams and symmetry, right? And setup in almost all of the problems you see me do, because those are the, you know, those are the parts that actually help students under, you know, frustration. Okay. So that is going to be it. But if this kind of explanation helps and you want more calculus and physics problems broken down this way in a systems type of approach, you can check out the full resources below. Okay, that will be in the description below. And my book, uh, Advanced Integration Techniques, can also help. Well, it's more of a mathematical methods book, but it talks about applications in electricity and magnetism if you want to learn more. Okay, that'll be in the link below as well. And if you want focused help with calculus, calculus, lots of ease, linear algebra, or things in like this, like mathematical physics, then tutoring information will also be in the link below. Use what helps. It's up to you. All right. And if you want more videos where hard exam problems become structured and readable, stay with the channel. There'll be much more interesting stuff coming soon. Right? Don't forget to like and subscribe. It really helps. Like and subscribe. See you in the next one, guys. Bye bye.